Hello, my name is Joe DalSanto, Professor of Astronomy at the College of DuPage in Glen Ellen, Illinois, and I'd like to welcome you to our course on solar system astronomy. We've got a lot of exciting things to learn about. I like to think of astronomy as an adventure of the mind, an opportunity for us to go places and learn things that we don't normally see here on Earth. Our solar system and the others we'll be examining have many wondrous things that have excited scientists throughout the world, but the point of our course is to share much of that with you, give you the opportunity to learn more about some of the exciting discoveries that we're making, as these things are not just for scientists, but for everyone. I've designed this course to be a concise introduction to solar system astronomy. I really like to share my excitement, my passion for astronomy with you. I hope that you'll enjoy the course, and I hope that you'll also consider perhaps our next course, which will deal with stars and galaxies. So what will our course deal with? Well, we're going to break the solar system into several regions. First, we'll look at the inner solar system. We'll consider the terrestrial planets, Mercury, Venus, Earth, Mars, and our moon. We'll look at other small bodies in the inner solar system, such as asteroids. Then we'll be progressing outward to the outer solar system, the large Jovian planets like Jupiter, Saturn, Uranus, Neptune. We'll finish up with an examination of small icy bodies in the outer solar system, things like comets, new objects that we found called Kuiper Belt objects, and yes, everybody's favorite, the planet Pluto. Our course will then conclude with a brief look at other solar systems. For centuries, mankind has wondered, could there be other planets in the universe? Well, today we know the answer is yes. And a whole new field has opened where we can examine and learn about these other solar systems. So we have much to learn, and I hope that you'll enjoy the ride along with me. Now, during the course, you'll notice PowerPoint slides pop up occasionally that will provide you a little bit more information and some images that will supplement the discussion. Many times we'll get more information from these, and that's your opportunity to pause the lecture if you like to examine those slides for a moment or two before continuing. Some of you might be a little bit concerned about a science course, thinking perhaps I'm not very good at math or I'm not very comfortable with math. Well, let me reassure you, you won't need any math for the course. There will be a little bit that I'll mention for those of you that perhaps have had some math and are comfortable with it, but for those that have not, again, you don't need to worry about the math. It's there merely to provide a little additional information. The course can be enjoyed without math. So how do we learn about the universe? Well, simply put, we use the scientific method. Science is a powerful and effective way for us to learn about the universe. Science looks for natural explanations for what we see in the universe. It progresses through the creation and testing of models or explanations of what's really happening in the universe. Those models, of course, need to be tested. We need to be able to determine if they're right or wrong, if they're correct or not. And that's what scientists do. They continue to make additional observations to see if our ideas are correct. And so science is a very progressive way to learn about the universe. If our model is correct, great. We'll continue to test it. We'll continue to learn more. We'll continue to make more observations. But if by chance it's not, if our observations show that the model is not correct, we may need to revise our model, improve it, change it, or in some cases we may need to abandon it and start over with a new way to look at our observations. Let's consider then a few steps in the process. I mentioned that it really starts with observations of the natural world. This normally generates questions. Why is this happening? How is it happening? Where is it happening? And in what manner is it happening? All these questions begin to naturally arise and get our minds thinking about what might explain what we're seeing. And so an explanation may begin to come to mind. We call this a hypothesis. What natural explanation might explain our observations? Once we have a hypothesis, Scientists, as I said, will then proceed to test the hypothesis. Think of a way to determine if this is correct or not. This may involve additional observations. It may involve other ways of going about that. Once again, if our observations and our tests confirm the model, great. We go on, we learn more. But on the other hand, if new observations disprove our model, we may need to revise or change or possibly even abandon our model. But ultimately, when we get an explanation that does seem to give us a correct view of our observations, this is when we begin to consider this a scientific theory. Now that word is used in everyday life, but often it's used in a different way. People may say, well, that's just your theory about a particular matter. That is not the way the word is used in science. In science, a theory is a tested explanation. Others, though, may say, well, that's okay, but I believe in facts. Just present the facts to me. So what is the difference between a fact and a theory? Well, a fact is a single proven piece of information that anyone can not only agree upon, but prove for themselves. A theory is built with facts. I like to illustrate it this way. Facts you might consider like bricks, but a theory might be considered like a house that you would build with the bricks. We take these facts and we assemble them in such a way that they provide us a structure in which to understand the universe. Now maybe you've heard of scientific laws. What are scientific laws? Well, a scientific law normally explains a relationship between two factors. I'll give you one example. We're going to be discussing the law of gravitation. And in this case, that law tells us how the strength of gravity changes with distance. So that helps us see more clearly how the natural world works. So to summarize, a scientific theory must do three things. Number one, it must explain our observations correctly. Number two, it must be supported by compelling evidence. And number three, it must not have failed any crucial test as to its validity. Once we have such a theory, we can be confident that it is correct. However, it's always open to further testing. Is it possible that someday the theory might be disproven? Yes, that is possible. But as of today, we have certain theories that we accept as an explanation for what we see in nature. Well, we're going to examine a number of different concepts in the course. I want to just very briefly touch on a few basic concepts that will help us in our discussion. Let's start with something as simple as motion. We're all very familiar with motion. We think of perhaps driving our cars. We cover a certain distance in a certain amount of time. Well, we'd consider that speed, but more precisely, scientists would use the term velocity. What happens if we change the velocity? We either speed up or slow down. We would consider that an acceleration. How about something called momentum? We all kind of have a feeling for that. We think of maybe driving your car on a rainy or snowy day and you say, boy, my car has a lot of momentum. It might not be very easy to stop the car. What is momentum? Well, technically it's defined as mass times velocity, but essentially momentum comes in two various forms, so to speak. One would be momentum or motion in a straight line, which again we think of a car perhaps. But in astronomy we have a type of momentum that is more a circular motion. And we call this angular momentum because the body is moving through an angle. Think perhaps of the Earth, again spinning on its axis. It has a certain angular momentum. Think perhaps of the Earth orbiting around the Sun. It has a certain angular momentum. So that type of concept will be important for us as we look at the solar system and how bodies move. We'll also be considering energy. Now there's three main types of energy that we'll be concerned about. Number one, we're all familiar perhaps with the energy of light. We stand outside on a sunny day, we feel the warm sunshine, we realize there's energy there. It can warm something up. Or these days, perhaps we take outside a solar panel, we capture the sunlight, and that device is able to change it into electricity. Well, that electricity can be used for various other purposes, and that leads us to our second type of energy, kinetic energy. What is kinetic energy? Well, this is energy of motion. Again, think of a car or an object in motion. This depends on the mass and on the velocity as well. We might think of perhaps taking that electricity from our solar panel, converting it to electricity, and perhaps it may drive our cars down the street. Or perhaps we use it to turn an electric motor that may move an object. So we can actually convert the radiative or light energy into the motion or kinetic energy. We have one more type of energy that's important in astronomy. It's called potential energy, and we think of that as stored energy. Here we might, again, store energy that's been captured from the sun in a battery. What can we do with that energy? Well, again, we might turn a motor, we might do other things with it. Or we may very simply take an object and use that electricity, use that energy to raise it to a higher level. Think perhaps of going to the amusement park. Maybe we get on the roller coaster and the electric motor takes that roller coaster up to a higher level, doesn't it? Well, you know what happens when they release you and the roller coaster begins to come down. It accelerates, it speeds up. Where does it get that kinetic energy? Well, it had stored energy, potential energy at the top of its path, and that again can be changed into kinetic energy. So we're just introducing some concepts here that are going to help us as we move along. We'll explain them a little further as we do go along. Another concept that will be important in our study of the solar system is gravity. Now, perhaps you associate that term with Isaac Newton. He first discovered that law long ago. We still use his equations as a very good approximation. There are better theories, frankly, but Isaac Newton's theory still works quite well as a good approximation of how gravity works. Newton discovered that two bodies have a naturally attractive force between them. And the strength of that force depends on how massive each body is and on the distance between them. So there's a very simple equation that describes this. Again, the larger the mass, the greater the force. The closer the distance, the greater the force. That will be important as we consider how the planets orbit the sun, how moons orbit planets, and so on and so forth. We'll also be very concerned with light. Light is very essential in astronomy. Why is that? Well, when you think about it, there's very few objects in astronomy that we can go study firsthand. We are able to send space probes to a few nearby objects, but we really can't necessarily go examine them up close. Instead, we have to rely on the light that we receive from those bodies to study them. Well, light has various properties. The ones we'll be interested in include wavelength, or how long or how large the light waves are, so to speak. We'll also talk about frequency, how quickly, how frequently the light wave passes by you. And we'll also talk about the energy of the light, as we mentioned a few minutes ago. Now, there's a very interesting relationship between the wavelength and the frequency. And mathematically, wavelength times frequency equals the speed of light. Now, the speed of light is a constant. It never changes. And so therefore, you can imagine that if the wavelength is a larger number, well, the frequency must be a lower number. In other words, if our frequency is lower, our wavelength is longer, and vice versa. If our wavelength is shorter or lower, our frequency must be higher. So you begin to see how these things work together, and we can utilize those again in our studies of astronomy. So you'll also see at the end of each lecture there'll be a brief review. Let me go ahead and review the few things we've talked about so far. What is needed to study astronomy, and in particular our solar system? Well, I think we mentioned at the beginning it starts with curiosity, doesn't it? We make observations of the natural world. Those observations lead us to ask questions. Those questions lead us into the steps of the scientific method. We begin to formulate an explanation, a hypothesis. We then test that hypothesis, whether it's correct or not, and eventually we hope to arrive at a true and correct explanation of what we've observed. We call that a theory. And we'll be seeing at least one and more theories as we move along. We touched on some basic concepts, didn't we? We looked at things like motion, energy, gravity, and light to kind of set the stage and give us some tools, so to speak, to be able to use in our exploration. And we did see at least one or more natural laws that will allow us to understand the universe. So we've got lots to look forward to. I'm glad to have you along. Hope you enjoy the course. Let's get started.